you ever wondered how some trains seem to float above the tracks, gliding smoothly without touching the rails? These are magnetic levitation or maglev trains. Today we'll uncover the fascinating science that allows these trains to hover and travel at incredible speeds. Let's start by understanding what makes maglev trains so unique compared to traditional trains, and why their floating ability is a game changer for transportation. Magnetic levitation is a method by which an object is suspended above another with no support other than magnetic fields. In maglev trains, this means the train floats above the tracks using powerful magnets. This eliminates friction between the train and the rails, allowing for a much smoother and faster ride. But how exactly do these magnets work together to achieve levitation? Let's break it down. Magnets are at the heart of maglev technology. There are two main types of magnets used: electromagnets and superconducting magnets. These magnets are strategically placed both on the train and along the track. By controlling the magnetic fields, engineers can make the train float, move forward, and even stop. The interaction between these magnets is what creates the levitating effect. Levitation occurs when the magnetic force pushing the train upwards balances out the force of gravity pulling it down. In maglev trains, this is achieved by arranging magnets so that like poles face each other, causing them to repel. This repulsion lifts the train off the track, allowing it to float. The gap between the train and the track is usually just a few centimeters, but it's enough to eliminate contact and friction. One common maglev system is called electromagnetic suspension, or EMS. In this system, electromagnets are placed on the train's underside, facing iron rails on the track. When powered, these magnets attract the train upwards, keeping it suspended just above the rails. Sensors constantly adjust the magnetic force to maintain a steady gap, ensuring a smooth and stable ride. Another maglev system is electrodynamic suspension, or EDS. Here, superconducting magnets on the train create strong magnetic fields that induce currents in coils along the track. These currents generate opposing magnetic fields, causing the train to be repelled and lifted above the track. EDS systems can maintain levitation even when the train is moving at high speeds, making them ideal for long-distance travel. Maintaining a stable and controlled levitation is crucial for passenger safety and comfort. Maglev trains use advanced sensors and computer systems to monitor the gap between the train and the track in real time. If the train gets too close or too far from the track, the system instantly adjusts the magnetic force to bring it back to the optimal position. This constant feedback ensures a smooth and safe ride. Because maglev trains float above the tracks, there's no physical contact between the train and the rails. This means there's almost no friction to slow the train down. As a result, maglev trains can reach much higher speeds than traditional trains, often exceeding 300 miles per hour. The lack of friction also reduces wear and tear, making maglev systems more durable and efficient. Levitation is just one part of the maglev story. To move forward, maglev trains use a system called linear motors. These motors create a moving magnetic field along the track which pulls or pushes the train forward. By precisely controlling the magnetic fields, the train can accelerate, decelerate, and stop smoothly, all without touching the rails. Maglev trains are known for their energy efficiency. Since there's no friction between the train and the track, less energy is needed to keep the train moving at high speeds. Additionally, regenerative braking systems can convert some of the train's kinetic energy back into electricity when slowing down, further improving efficiency and reducing energy consumption. Safety is a top priority for maglev systems. The trains are designed with multiple redundant systems to ensure safe operation. For example, if one set of magnets fails, backup systems can take over instantly. The tracks are also equipped with sensors to detect any obstacles or issues, and the trains can be brought to a stop quickly if needed. These features make maglev one of the safest forms of high-speed travel. Maglev trains are already in operation in several countries. For instance, the Shanghai Maglev in China is one of the fastest commercial trains in the world, reaching speeds up to 267 miles per hour. Japan's Chuo Shinkansen is another example, using superconducting maglev technology for even higher speeds. These real-world systems showcase the potential and reliability of maglev technology. Maglev trains offer numerous benefits over traditional rail systems. They are faster, quieter, and require less maintenance due to the lack of physical contact. The smooth ride improves passenger comfort, and the reduced energy consumption makes them more environmentally friendly. As technology advances, maglev trains could become a key part of future transportation networks. Despite their advantages, maglev trains face some challenges. Building maglev tracks is expensive and the technology requires significant investment. Compatibility with existing rail infrastructure is also an issue, as maglev trains need dedicated tracks. However, ongoing research and development are working to overcome these obstacles, making maglev more accessible in the future. As we look ahead, maglev technology holds great promise for revolutionizing transportation. With ongoing advancements in materials, energy efficiency, and safety, maglev trains could become more widespread and affordable. Imagine a world where cities are connected by floating trains, making travel faster, cleaner, and more convenient for everyone. The science behind maglev is not just fascinating, it's paving the way for the future of travel.